What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this, a vast, endless expanse where galaxies stretch farther than the eye can see, and yet we've only scratched the surface of understanding what lies beyond. What if the very fabric of reality is hiding secrets that could rewrite the rules of space, time, and existence itself? Today, we're diving into the 25 greatest mysteries of the expanding universe, enigmas that defy our current knowledge and challenge the very limits of human understanding. From the invisible forces shaping the cosmos to the mind-bending questions about what lies beyond the edge of the observable universe, these mysteries are not just scientific puzzles, they're gateways to a deeper understanding of reality. So buckle up, because we're about to take you on a journey through the cosmos, where every discovery raises more questions than answers, and where the universe itself becomes the ultimate mystery waiting to be unraveled. Stay with us, because by the end of this video, you'll see the universe in a way you never have before. Now turning to the first of our cosmic mysteries, we encounter the enigma of dark energy, a force so mysterious that it makes up about 68% of the universe, yet we know almost nothing about it. Dark energy is the invisible hand pushing the universe to expand faster and faster, defying the pull of gravity that should be slowing things down. This discovery came about in the late 1990s when astronomers observed distant supernovae and realized they were fainter than expected. This meant the universe wasn't just expanding, it was accelerating. The implications are staggering. If dark energy continues to dominate, the universe could expand forever, leading to a cold, dark, and empty future known as the Big Freeze. But what exactly is dark energy? One leading theory is the cosmological constant, an idea first proposed by Albert Einstein, which suggests that empty space itself has an inherent energy that drives expansion. Yet this theory raises more questions than answers. Why does dark energy have the specific value it does, and why does it dominate the universe now rather than earlier in cosmic history? Despite decades of research, dark energy remains one of the greatest unsolved problems in physics, a puzzle that could redefine our understanding of the cosmos. As we move forward, this mystery will continue to challenge scientists, pushing the boundaries of what we know about the universe and its ultimate fate. Now turning to the second of our cosmic mysteries, we delve into the shadowy realm of dark matter, an invisible substance that makes up roughly 27% of the universe. Unlike dark energy, which pushes the universe apart, dark matter acts as a cosmic glue, holding galaxies and galaxy clusters together through its gravitational pull. We can't see it, touch it, or detect it directly, yet its presence is undeniable. How do we know it's there? The answer lies in the way galaxies behave. Stars on the outer edges of galaxies rotate faster than they should if only the visible matter were pulling them. This discrepancy points to the existence of an unseen mass, dark matter, exerting its gravitational influence. Similarly, when we observe galaxy clusters, the way they bend light from background objects, a phenomenon known as gravitational lensing, reveals the presence of far more mass than what's visible. But what exactly is dark matter? Scientists have proposed several theories, with two leading candidates being WIMP, or weakly interacting massive particles, and actions. WIMP are hypothetical particles that interact weakly with ordinary matter, making them incredibly difficult to detect. Actions, on the other hand, are ultra-light particles that could explain dark matter's elusive nature. To uncover the truth, researchers are conducting groundbreaking experiments. Particle colliders, like the Large Hadron Collider, are smashing atoms together in hopes of creating dark matter particles. Meanwhile, deep underground detectors, shielded from cosmic interference, are searching for faint signals of dark matter interactions. Despite these efforts, dark matter remains one of the most profound mysteries in modern science. Its discovery would not only solve a cosmic puzzle, but also revolutionize our understanding of the universe's structure and evolution. As we continue to probe the depths of space, the quest to uncover the true nature of dark matter remains a driving force in our exploration of the cosmos. Now turning to the third mystery of the cosmos, we journey back to the very beginning, the moment of the universe's birth, known as the Big Bang Singularity. This is the point where all matter, energy, space, and time were compressed into an infinitely dense and hot state. It's a concept that defies our current understanding of physics, as both general relativity and quantum mechanics break down when trying to describe it. General relativity, which explains gravity and the large-scale structure of the universe, predicts that the singularity was a point of infinite density. But infinity is not a number we can work with in physics. It's a sign that our theories are incomplete. On the other hand, quantum mechanics, which governs the behavior of particles at the smallest scales, also fails to provide answers. At the singularity, the universe was smaller than an atom, yet quantum effects should have been dominant, but we still lack a unified theory that combines these two frameworks to explain what truly happened at the Big Bang. To address this puzzle, scientists have proposed alternative theories. One such idea is the Big Bounce, which suggests that the Big Bang wasn't the beginning but rather a rebound from a previous collapsing universe. In this scenario, the universe cycles through endless expansions and contractions, avoiding the singularity altogether. Another intriguing possibility is the multiverse theory, which posits that our universe is just one of many in a vast cosmic landscape. In this view, the Big Bang might have been a local event within a larger, eternal multiverse. While these theories offer fascinating alternatives, they remain speculative as we lack the observational evidence to confirm them. The Big Bang Singularity remains one of the most profound mysteries in cosmology, challenging us to rethink our understanding of space, time, and reality itself. As we continue to explore the cosmos, the quest to unravel the true nature of the universe's birth remains at the forefront of scientific inquiry. Now turning to the fourth mystery of the cosmos, we encounter the horizon problem, a puzzle that challenges our understanding of the universe's uniformity. When we look out into the cosmos, we see that the universe appears remarkably similar in all directions. The temperature of the cosmic microwave background, the afterglow of the Big Bang, is nearly identical everywhere we observe, down to tiny fractions of a degree. But here's the catch. Regions of the universe that are now far apart were, in the early universe, so distant from each other that light, or any form of communication, could not have traveled between them in the time since the Big Bang. This raises a profound question. How did these regions come to be so uniform if they never had a chance to interact or exchange information? To solve this mystery, scientists propose the concept of cosmic inflation. This theory suggests that in the earliest moments of the universe, just a tiny fraction of a second after the Big Bang, space underwent an incredibly rapid expansion. Imagine blowing up a balloon to an enormous size in an instant. During this inflationary phase, regions that were once close together were suddenly stretched far apart, creating the vast, uniform cosmos we observe today. Inflation not only explains the uniformity of the universe, but also accounts for the tiny fluctuations in density that eventually gave rise to galaxies and large-scale structures. The evidence for cosmic inflation comes from the cosmic microwave background, the faint glow of radiation left over from the Big Bang. Detailed measurements of this radiation reveal patterns that match the predictions of inflation, such as the slight variations in temperature and the distribution of matter. These observations provide strong support for the idea that the universe underwent a rapid expansion phase. However, inflation is not without its challenges. While it explains many features of the universe, the exact mechanism that triggered and ended inflation remains unknown. What caused this sudden expansion? And why did it stop? These are questions that continue to puzzle scientists. As we delve deeper into the horizon problem, we are reminded of how much we still have to learn about the early universe. Cosmic inflation offers a compelling solution, but it also opens the door to new mysteries, pushing us to refine our theories and seek out new evidence. The quest to understand the universe's uniformity is far from over, and each discovery brings us closer to unraveling the secrets of our cosmic origins. Now turning to the fifth mystery of the cosmos, we encounter the puzzling case of the missing baryons. When scientists calculate the total amount of ordinary matter, or baryons, that should exist in the universe based on the Big Bang's predictions, they find a significant discrepancy. According to these calculations, only about half of the expected baryons have been observed. So, where is the rest of this ordinary matter hiding? The answer lies in the vast, intricate structure of the cosmic web, a network of filaments made up of hot, diffuse gas that stretches across the universe. These filaments, though incredibly thin and difficult to detect, are thought to contain the missing baryons. The gas is so hot that it emits X-rays, but it's also so spread out that it's nearly invisible to traditional telescopes. To uncover this hidden matter, astronomers rely on advanced tools and techniques. One key method involves using powerful X-ray telescopes, such as the Chandra X-ray Observatory, to detect the faint glow of this hot gas. By observing the way X-rays are absorbed and emitted by these filaments, scientists can map their distribution and estimate the amount of matter they contain. Another approach uses simulations of the universe's large-scale structure, which predict how baryons should be distributed based on the laws of physics. These simulations help guide observations and provide a framework for interpreting the data. Despite these efforts, the search for the missing baryons remains a challenge. The gas filaments are incredibly faint, and their signals are often drowned out by other sources of X-rays in the universe. However, recent advancements in telescope technology and data analysis are bringing us closer to solving this mystery. By combining observations from multiple wavelengths of light and refining their simulations, astronomers are gradually piecing together the puzzle of the missing baryons. As we explore this cosmic enigma, we are reminded of how much of the universe remains hidden from our view. The missing baryons are not just a gap in our understanding, they are a testament to the complexity and vastness of the cosmos. Each discovery brings us closer to a complete picture of the universe's matter, and with it, a deeper understanding of the forces that shape our existence. The search continues, driven by curiosity and the relentless pursuit of knowledge. Now turning to the sixth mystery of the cosmos, we encounter a peculiar and somewhat humorous anomaly known as the axis of evil. This term, coined by scientists, refers to an unexpected alignment of temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang. These fluctuations, which are tiny variations in temperature, are supposed to be randomly distributed across the sky. However, observations reveal a strange pattern. Some of these fluctuations appear to align along a specific axis, creating a structure that defies expectations. This alignment challenges the standard model of cosmology, which assumes that the universe is isotropic, meaning it looks the same in all directions. The presence of the axis of evil suggests that there might be something fundamentally different about the universe's structure, or that our understanding of its origins is incomplete. Some scientists speculate that this anomaly could hint at new physics, such as a previously unknown force or a modification to our theories of gravity. Others argue that it might simply be a statistical fluke, a random alignment that appears significant due to the limitations of our observations. To investigate this mystery, researchers analyze data from missions like the Planck satellite, which has mapped the cosmic microwave background with unprecedented precision. By studying the distribution of temperature fluctuations, they hope to determine whether the axis of evil is a real feature of the universe or an artifact of measurement errors or incomplete data. The implications of this anomaly are profound. If it points to new physics, it could revolutionize our understanding of the cosmos. If it's a fluke, it serves as a reminder of how complex and unpredictable the universe can be. As we delve into this cosmic puzzle, we are reminded that even the most well-established theories can be challenged by unexpected discoveries. The axis of evil is not just a quirky name, it's a symbol of the mysteries that still await us in the vast expanse of the universe. Each observation, each anomaly, brings us closer to unraveling the true nature of reality, and with it, a deeper appreciation for the wonders that lie beyond our current understanding. The search for answers continues, driven by the same curiosity that has guided humanity's exploration of the cosmos for centuries. Now turning to the seventh mystery of the cosmos, we encounter a gravitational enigma known as the Great Attractor. This mysterious force is pulling not just our Milky Way galaxy, but thousands of others toward a specific region of space. Imagine a cosmic tug of war where entire galaxies are being drawn toward an unseen point, as if the universe itself has a hidden magnet. The Great Attractor lies approximately 250 million light-years away, but its exact nature remains shrouded in mystery, largely because it's located behind the dense plane of the Milky Way. This region, filled with stars, gas, and dust, obscures our view, making it incredibly challenging to study directly. Despite these obstacles, astronomers have pieced together clues about what might be causing this immense gravitational pull. One leading theory suggests that the Great Attractor could be a massive supercluster of galaxies, a dense gathering of thousands of galaxies bound together by gravity. These superclusters are among the largest structures in the universe, and their combined mass could generate the gravitational force needed to pull galaxies toward them. Another possibility is that dark matter, the invisible substance that makes up a significant portion of the universe, is concentrated in this region, creating a gravitational well that draws galaxies inward. To better understand the Great Attractor, scientists use advanced tools like X-ray telescopes and infrared observations, which can peer through the Milky Way's obscuring dust. These instruments have revealed hints of massive structures, such as the Norma cluster, which may be part of the Great Attractor's influence. Yet, even with these discoveries, the full picture remains elusive. Some researchers speculate that the Great Attractor might not be the final destination, but rather a stepping stone toward an even larger structure, such as the Shapley supercluster, located even farther away. The Great Attractor serves as a reminder of how much we still have to learn about the universe's large-scale structure. It challenges us to refine our tools and theories, pushing the boundaries of our knowledge. As we continue to explore this cosmic mystery, we are drawn not just by the force of gravity, but by the enduring human desire to uncover the secrets of the cosmos. Each discovery brings us closer to understanding the forces that shape our universe and our place within it. Now turning to the eighth mystery of the cosmos, we encounter a puzzling discrepancy known as the Hubble tension. This mystery revolves around the universe's expansion rate, a fundamental value in cosmology called the Hubble constant. For decades, scientists have used two primary methods to measure this rate. The first involves observing distant supernovae and galaxies to calculate how fast they are moving away from us. The second method relies on the cosmic microwave background, the faint afterglow of the Big Bang, to infer the expansion rate from the early universe. Here's where the tension arises. These two methods, though both precise and well-established, give different results. The cosmic microwave background suggests a slower expansion rate, while observations of nearby galaxies and supernova indicate a faster one. This discrepancy has left scientists scratching their heads as it challenges our understanding of the universe's evolution. If both methods are correct, why don't they agree? Could there be something missing in our current models of cosmology? One possibility is that dark energy, the mysterious force driving the universe's accelerated expansion, is not constant but evolves over time. This would mean that the expansion rate has changed in ways we don't yet fully understand. Another intriguing idea is that there might be undiscovered particles or forces at play, influencing the universe's expansion in ways we haven't accounted for. These scenarios would require new physics, potentially rewriting some of the fundamental principles we rely on to explain the cosmos. The Hubble tension isn't just a technical disagreement, it's a profound mystery that could reshape our understanding of the universe. It highlights the gaps in our knowledge and pushes scientists to refine their measurements and theories. As researchers continue to investigate, they are developing new techniques, such as using gravitational waves or studying the distribution of galaxies to resolve this tension. Each step brings us closer to uncovering the truth, but for now, the Hubble tension remains one of the most compelling puzzles in modern cosmology. This mystery reminds us that even the most fundamental aspects of the universe can hold surprises. As we strive to measure the cosmos with ever greater precision, we are constantly reminded of how much there is still to learn. The Hubble tension isn't just a challenge for scientists, it's an invitation to explore the unknown and deepen our understanding of the universe's grand story. Now turning to the ninth mystery of the cosmos, we delve into the enigmatic nature of black holes. These cosmic phenomena, born from the collapse of massive stars, are regions of spacetime where gravity is so intense that nothing, not even light, can escape. At the heart of every black hole lies a singularity, a point where the laws of physics as we know them break down and our understanding of reality reaches its limits. One of the most fascinating aspects of black holes is their event horizon, the boundary beyond which escape is impossible. Crossing this threshold means entering a realm where time and space behave in ways that defy intuition. But the mysteries don't end there. Black holes also present us with the information paradox, a puzzle that has stumped physicists for decades. According to quantum mechanics, information about the state of matter cannot be destroyed. Yet, when matter falls into a black hole, it seems to vanish completely, leaving no trace. How can these two ideas coexist? This paradox suggests that our current theories of gravity and quantum mechanics are incomplete, and resolving it may require a new framework that unites the two. Recent breakthroughs have brought us closer to understanding these cosmic enigmas. In 2019, the Event Horizon Telescope collaboration unveiled the first ever image of a black hole, capturing the shadow of the supermassive black hole at the center of the galaxy Messier 87. This historic achievement not only confirmed the existence of black holes, but also provided a glimpse into their structure and behavior. Yet many questions remain unanswered. What lies inside a black hole? What happens to matter as it approaches the singularity? And what does the existence of black holes tell us about the nature of spacetime itself? Some theories suggest that black holes might not be the ultimate endpoints of matter, but could instead serve as gateways to other regions of the universe or even other universes entirely. Others propose that the singularity at the core of a black hole might be replaced by something entirely different, such as a quantum bridge or a region of extreme spacetime curvature. These ideas push the boundaries of our imagination and challenge us to rethink the very fabric of reality. The nature of black holes is a mystery that continues to captivate scientists and the public alike. As we explore these cosmic giants, we are not only uncovering the secrets of the universe, but also testing the limits of human knowledge. Each discovery brings us closer to understanding the profound connections between gravity, quantum mechanics, and the nature of existence itself. And as we peer into the depths of these enigmatic objects, we are reminded that the universe is far stranger and more wondrous than we could ever imagine. Now turning to the 10th mystery of the cosmos, we confront one of the most perplexing questions in science, the Fermi paradox. Named after physicist Enrico Fermi, this paradox highlights the stark contradiction between the high probability of extraterrestrial civilizations existing in the universe and the complete lack of evidence for their existence. With billions of galaxies, each containing billions of stars and planets, Why haven't we detected any signs of intelligent life beyond Earth? One possible explanation is the rarity of intelligent life. While the universe may be teeming with planets capable of supporting life, the emergence of complex, intelligent civilizations might be an extraordinarily rare event. The conditions required for life to evolve, develop technology, and communicate across interstellar distances could be so specific that Earth is one of the few, or even the only, places where this has happened. Another grim possibility is that intelligent civilizations tend to self-destruct before they can develop the technology needed for interstellar communication or travel. Whether through war, environmental collapse, or other catastrophic events, advanced societies might inevitably reach a point where they destroy themselves, leaving no trace for others to find. Alternatively, advanced civilizations might exist but are deliberately avoiding contact with us. They could be using technology far beyond our comprehension, making them invisible to our current methods of detection. Some theories suggest that these civilizations might be observing us from a distance, choosing not to interfere, or perhaps they have moved beyond the need for physical communication altogether, existing in forms we cannot yet perceive. There's also the possibility that we are simply looking in the wrong way or in the wrong places. Our search for extraterrestrial intelligence has been limited to a narrow range of methods, such as scanning for radio signals. Advanced civilizations might use entirely different forms of communication that we have yet to discover or understand. The Fermi paradox challenges us to rethink our assumptions about life, intelligence, and the nature of the universe. It forces us to consider not only the possibility of other civilizations, but also the fragility and uniqueness of our own. As we continue to explore the cosmos, this paradox reminds us that the answers we seek might be far stranger than we imagine, and that the universe still holds countless mysteries waiting to be unraveled. Now turning to the 11th mystery of the cosmos, we venture into the mind-bending realm of the multiverse hypothesis. This idea suggests that our universe might not be the only one instead. It could be just one of countless others, each with its own unique laws of physics, dimensions, and even realities. Imagine a cosmic tapestry where every possible outcome, every alternate history, and every variation of existence plays out in parallel universes. It's a concept that stretches the boundaries of our imagination and challenges our understanding of reality itself. One of the most intriguing multiverse theories is the idea of bubble universes. Picture the early universe as a frothy sea of energy where tiny bubbles form and expand. Each bubble could be its own universe with its own distinct properties. Some might have stars and galaxies like ours, while others could be entirely alien, governed by forces we can't even comprehend. These bubble universes are thought to exist in a vast, ever-expanding cosmic landscape, forever out of reach from one another. Another fascinating theory comes from string theory, which proposes that our universe is just one of many possible configurations in a higher dimensional space called the string theory landscape. In this view, the fundamental constants of nature, like the strength of gravity or the mass of particles, could vary from one universe to another. This means that somewhere out there might be a universe where gravity is weaker, or where atoms behave in ways we can't even imagine. Then there's the quantum many-worlds interpretation, which suggests that every time a quantum event occurs, like the decay of an atom or the flip of a particle's spin, the universe splits into multiple branches. In one branch, the atom decays, in another, it doesn't. This means that every possible outcome of every quantum event creates a new universe, leading to an infinite number of parallel realities. It's a dizzying idea, but one that some physicists take seriously as a way to explain the strange behavior of particles at the quantum level. Of course, testing these ideas is no easy task. The multiverse, by its very nature, exists beyond the reach of our telescopes and detectors. How do we study something that might be completely disconnected from our own universe? Some scientists are looking for subtle clues in the cosmic microwave background, the faint afterglow of the Big Bang, which might carry imprints of collisions between our universe and others. Others are exploring the mathematical consistency of these theories, searching for ways to make predictions that could one day be tested. The multiverse hypothesis forces us to confront profound questions about the nature of reality. If there are infinite universes, does that mean every possible version of ourselves exists somewhere? What does it mean for our understanding of existence if our universe is just one tiny piece of a much larger puzzle? These questions might seem abstract, but they push the boundaries of science and philosophy, challenging us to think beyond the limits of what we know. As we continue to explore the mysteries of the cosmos, the multiverse hypothesis reminds us that the universe or universes might be far stranger and more complex than we ever imagined. It's a reminder that the search for knowledge is never ending, and that the answers we seek might lie in realms we have yet to discover. Now turning to the 12th mystery of the cosmos, we confront one of the most profound questions of all. How will the universe end? The fate of everything we know, galaxies, stars, planets, and even life itself hinges on the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. While we can't predict the future with certainty, scientists have proposed several possible scenarios, each more dramatic than the last. One of the leading theories is the Big Freeze, also known as the heat death of the universe. In this scenario, dark energy continues to push galaxies apart at an ever-increasing rate. Over trillions of years, stars will burn out, galaxies will drift so far apart that they become invisible to one another, and the universe will grow colder and darker. Eventually, all that will remain is a vast, empty expanse where even the last remnants of heat and light fade into nothingness. It's a chilling thought, but one that aligns with our current understanding of dark energy's relentless influence. On the other hand, there's the Big Crunch, a scenario where the expansion of the universe slows down and eventually reverses. If dark energy weakens over time, gravity could take over, pulling everything back together in a cosmic collapse. Galaxies would rush toward one another, stars and planets would collide, and the universe would shrink back into an infinitely dense point, a mirror image of the Big Bang. Some scientists speculate that this could even trigger a new Big Bang, creating a cyclical universe that expands and contracts in an endless loop. Then there's the Big Rip, perhaps the most dramatic of all. In this scenario, dark energy doesn't just accelerate the expansion of the universe, it grows stronger over time. Eventually, its force would become so powerful that it tears apart galaxies, stars, planets, and even atoms themselves. The universe would end not with a whimper, but with a violent, all-encompassing rupture. While this might sound like science fiction, it's a real possibility if dark energy behaves in a certain way. The key to understanding which of these scenarios will unfold lies in the nature of dark energy. Is it a constant force, as Einstein's cosmological constant suggests, or does it change over time, growing stronger or weaker as the universe evolves? These are questions that cosmologists are racing to answer, using tools like the James Webb Space Telescope and large-scale surveys of the universe's structure. The answers could reshape our understanding of the cosmos and its ultimate destiny. As we ponder the end of the universe, we're reminded of the fragility and impermanence of everything we know. Whether the cosmos ends in a freeze, a crunch, or a rip, it's a reminder that the universe is a dynamic, ever-changing place. And while the end might seem distant, it's a question that challenges us to think deeply about the nature of existence and our place within it. The search for answers continues, and with each discovery, we come one step closer to unraveling the ultimate fate of the cosmos. Now turning to the 13th mystery of the cosmos, we delve into the puzzling case of the Pioneer anomaly. In the late 20th century, as the Pioneer 10 and 11 spacecraft ventured beyond the outer planets, scientists noticed something strange. Both spacecraft were slowing down slightly more than expected, as if an unseen force was gently tugging them back toward the sun. This unexpected deceleration, though tiny, defied the predictions of Newtonian physics and Einstein's theory of general relativity. It became one of the most intriguing mysteries in space exploration, sparking decades of debate and investigation. One of the leading explanations for the Pioneer anomaly involves thermal radiation. The spacecraft were powered by radioactive plutonium, which generated heat as it decayed. Some scientists propose that this heat, radiating unevenly from the spacecraft, could have created a tiny but measurable thrust, slowing them down. While this theory seemed plausible, detailed calculations and simulations revealed that thermal radiation alone couldn't fully account for the observed deceleration. The mystery deepened, leaving researchers to consider more exotic possibilities. Could the Pioneer anomaly be evidence of new physics? Some theorists suggested that the anomaly might hint at modifications to our understanding of gravity, such as deviations from Einstein's theory on large scales. Others speculated about the influence of dark matter or even unknown forces acting within the solar system. While these ideas are fascinating, they remain speculative, as no definitive evidence has been found to support them. The Pioneer anomaly continues to challenge our understanding of the laws that govern the cosmos. Despite decades of study, the Pioneer anomaly remains unresolved. The spacecraft themselves are now too far away and too faint to provide new data, leaving scientists to rely on historical records and simulations. Yet, the mystery has inspired new missions and technologies designed to test the limits of our knowledge. For example, future spacecraft could be equipped with more precise instruments to measure even the tiniest forces acting on them, potentially shedding light on this cosmic puzzle. The Pioneer anomaly serves as a reminder that even in our own solar system, there are still mysteries waiting to be solved. It challenges us to question our assumptions, refine our theories, and explore the unknown with curiosity and determination. As we continue to probe the depths of space, anomalies like this remind us that the universe is full of surprises, and every discovery brings us closer to understanding the true nature of reality. Now turning to the 14th mystery of the cosmos, we encounter one of the most tantalizing enigmas in the search for extraterrestrial intelligence, the WOW signal. In August 1977, a radio telescope at Ohio State University detected a powerful, narrowband signal from deep space that lasted for 72 seconds. The signal was so unusual and unexpected that astronomer Jerry Amon circled it on the printout and wrote "Wow" next to it, giving the phenomenon its iconic name. To this day, the WOW signal remains unexplained, sparking endless speculation and debate about its origin. The signal appeared to come from the direction of the constellation Sagittarius, and its frequency matched the hydrogen line, a frequency that scientists had long considered a likely candidate for interstellar communication. This alignment fueled hopes that the WOW signal might be a deliberate message from an extraterrestrial civilization. However, despite numerous attempts to detect the signal again, it has never been observed since. This fleeting nature has made it both a source of fascination and frustration for researchers. One of the biggest challenges in verifying the WOW signal is the lack of repeatability. In science, a single observation is rarely enough to draw definitive conclusions. Without additional data or a repeat signal, it's impossible to confirm whether the WOW signal was a genuine extraterrestrial transmission or something more mundane, such as interference from a human-made source or a natural cosmic phenomenon. The mystery is further complicated by the fact that the signal was detected by only one telescope, making it difficult to rule out local anomalies or equipment errors. Despite these challenges, the WOW signal has inspired ongoing efforts to search for similar signals. Projects like the Search for Extraterrestrial Intelligence, or SETI, continue to scan the skies for signs of intelligent life, using advanced technology and algorithms to sift through vast amounts of data. The wow signal serves as a reminder of the importance of persistence and open-mindedness in the search for answers. It also highlights the immense difficulty of distinguishing between a potential alien message and the countless other signals that fill the cosmos. The implications of the wow signal extend far beyond astronomy. If it were ever confirmed as a message from an extraterrestrial civilization, it would fundamentally alter our understanding of humanity's place in the universe. It would raise profound questions about the nature of intelligence, the likelihood of life beyond Earth, and the possibility of interstellar communication. Even if the signal remains unexplained, it continues to inspire curiosity and wonder, reminding us that the universe is vast, mysterious, and full of possibilities. As we ponder the wow signal, we are reminded that the search for intelligent life is not just about finding answers, it's about asking the right questions. Every unexplained signal, every anomaly, and every mystery pushes us to refine our methods, expand our knowledge, and explore the cosmos with renewed determination. The wow signal may remain a mystery for now, but it stands as a beacon of hope and curiosity in our ongoing quest to understand the universe and our place within it. Now turning to the 15th mystery of the cosmos, we venture into the outer reaches of our solar system to explore a puzzling phenomenon known as the Kuiper Cliff. Beyond the orbit of Neptune lies the Kuiper Belt, a vast region filled with icy bodies and dwarf planets like Pluto. But as astronomers map this distant frontier, they've noticed something strange. Beyond a certain distance, the number of objects in the Kuiper Belt drops off dramatically. This sudden boundary, often referred to as the Kuiper Cliff, has left scientists scratching their heads and searching for answers. The Kuiper Cliff is located roughly 4.8 billion kilometers from the Sun, and its existence challenges our understanding of how the solar system formed. According to current models, the Kuiper Belt should gradually thin out as you move farther from the Sun, but the abrupt drop-off suggests something unusual is at play. One leading theory is that an undiscovered planet, sometimes called Planet 9, could be lurking in the outer solar system, its gravitational influence carving out this sharp edge. This hypothetical planet, if it exists, would be several times more massive than Earth and could explain not only the Kuiper Cliff but also the peculiar orbits of some distant objects. Another possibility is that the Kuiper Cliff is the result of a past collision or series of collisions that disrupted the distribution of objects in the belt. Such an event could have scattered or destroyed many of the icy bodies beyond a certain distance, leaving behind the stark boundary we observe today. Alternatively, some scientists suggest that the Kuiper Cliff might be a relic of the solar system's early days, a frozen snapshot of the conditions that existed as the planets were forming. If this is the case, studying the cliff could provide valuable clues about the processes that shaped our cosmic neighborhood. The mystery of the Kuiper Cliff has profound implications for our understanding of the solar system's history and evolution. If an undiscovered planet is responsible, it would be one of the most significant astronomical discoveries in decades, reshaping our knowledge of the outer solar system. On the other hand, if the cliff is the result of ancient collisions or primordial conditions, it could shed light on the chaotic environment of the early solar system and the forces that shaped its current structure. As we continue to explore the Kuiper Belt with advanced telescopes and space missions, the Kuiper Cliff remains a tantalizing enigma. It reminds us that even in our own cosmic backyard, there are still mysteries waiting to be unraveled. Whether the answer lies in a hidden planet, a long-forgotten collision, or something entirely unexpected, the Kuiper Cliff challenges us to rethink what we know about the solar system and inspires us to keep searching for answers in the vast, icy expanse beyond Neptune. Now turning to the 16th mystery of the cosmos, we journey even farther from the Sun, beyond the Kuiper Belt, to explore the enigmatic Oort cloud. This vast, hypothetical shell of icy bodies is thought to encircle our solar system at an astonishing distance, stretching nearly halfway to the nearest star. The Oort cloud is believed to be the birthplace of long-period comets, those icy wanderers that occasionally streak through the inner solar system, leaving behind glowing tails that captivate stargazers. Despite its immense size, the Oort cloud remains one of the most elusive features of our solar system. Its extreme distance ranging from around 2,000 to as much as 100,000 times the distance between Earth and the Sun makes it nearly impossible to observe directly. Unlike the Kuiper belt, where telescopes have spotted countless objects, the Oort cloud's inhabitants are too faint and too far away to be seen with current technology. Instead, its existence is inferred from the orbits of comets that appear to originate from this distant region. The Oort cloud is thought to be a frozen archive of the solar system's earliest days, preserving remnants of the material that formed the planets over 4.5 billion years ago. These icy bodies were likely flung outward by the gravitational influence of the giant planets, settling into a vast, diffuse cloud that marks the outermost boundary of the Sun's gravitational influence. Studying the Oort cloud could provide invaluable insights into the conditions and processes that shaped our solar system during its infancy. One of the most intriguing aspects of the Oort cloud is its potential role as a gateway for interstellar visitors. Some scientists speculate that objects from other star systems could become trapped in the Oort cloud as they pass through our cosmic neighborhood. In fact, the discovery of interstellar objects like Oumuamua and Borisov has fueled speculation that the Oort cloud might harbor more such visitors, offering a unique opportunity to study material from beyond our solar system. The challenges of observing the Oort cloud are immense, but advancements in technology and space exploration may one day allow us to probe this distant frontier. Missions designed to travel beyond the outer planets could provide new data, while next-generation telescopes might detect faint signals from the cloud's icy inhabitants. Unlocking the secrets of the Oort cloud could not only deepen our understanding of the solar system's origins, but also reveal clues about the broader universe and our place within it. As we ponder the mysteries of the Oort cloud, we are reminded of the vastness of space and the countless wonders that lie beyond our current reach. This distant, icy realm challenges us to push the boundaries of exploration and inspires us to keep searching for answers in the farthest reaches of our cosmic home. Now turning to the 17th mystery of the cosmos, we shift our gaze inward toward the heart of our own galaxy, the Milky Way. At its center lies a region teeming with strange and unexplained phenomena that challenge our understanding of the universe. The galactic center is a place of extremes where gravity, radiation, and mysterious forces collide in ways that continue to baffle scientists. One of the most puzzling features of the galactic center is the presence of intense gamma-ray emissions. These high-energy bursts of radiation seem to originate from a region surrounding the supermassive black hole known as Sagittarius, a star. While black holes are known to emit radiation as they consume matter, the sheer intensity and irregular patterns of these gamma rays defy conventional explanations. Some researchers suggest that the emissions could be caused by the annihilation of dark matter particles, a process that would release vast amounts of energy. Others propose that exotic physics beyond our current understanding might be at play. Adding to the mystery are the fast radio bursts detected from the galactic center. These brief, intense pulses of radio waves last only milliseconds but pack an extraordinary amount of energy. While fast radio bursts have been observed in other parts of the universe, their occurrence at the heart of the Milky Way raises new questions. Could they be linked to the supermassive black hole, or are they the result of interactions between dense stellar remnants such as neutron stars? The answers remain elusive, but each discovery brings us closer to unraveling the secrets of this enigmatic region. The galactic center is also home to a dense cluster of stars, orbiting at incredible speeds around Sagittarius, a star. The gravitational forces at play here are so extreme that they warp spacetime itself, creating conditions unlike anywhere else in the galaxy. Some scientists speculate that these extreme environments could be testing grounds for new physics, offering clues about the nature of gravity, dark matter, and even the fabric of the universe. As we continue to study the galactic center, we are reminded of how much we still have to learn about the cosmos. The anomalies observed here challenge our theories and push the boundaries of human knowledge. With each new observation and technological advancement, we inch closer to understanding the forces that shape the heart of our galaxy, and by extension, the universe itself. The mysteries of the galactic center are a testament to the enduring allure of space, inviting us to explore, question, and discover. Now turning to the 18th mystery of the cosmos, we venture into the realm of ultra-high-energy cosmic rays, particles that travel through space at nearly the speed of light and strike Earth with astonishing force. These cosmic rays, some of the most energetic particles in the universe, carry millions of times more energy than anything we can produce in particle accelerators on Earth. Yet, despite their immense power, their origins remain one of the greatest puzzles in astrophysics. The challenge of tracing the sources of these cosmic rays lies in their nature. Unlike light, which travels in straight lines, cosmic rays are charged particles, meaning they are deflected by magnetic fields as they journey through space. By the time they reach Earth, their paths are so twisted that pinpointing their exact origin is nearly impossible. This makes it incredibly difficult to determine where these particles are coming from and what cosmic events could be producing them. Scientists have proposed several theories to explain the origins of ultra-high-energy cosmic rays. One leading idea is that they are produced by cataclysmic events in distant galaxies, such as supernova explosions or the collision of neutron stars. These violent processes could accelerate particles to incredible speeds, sending them hurtling across the universe. Another possibility is that they originate from the vicinity of supermassive black holes, where the intense gravitational and magnetic fields could act as natural particle accelerators. There is also the tantalizing possibility that these cosmic rays come from entirely unknown cosmic processes. Some researchers speculate that they could be linked to exotic phenomena, such as the decay of hypothetical particles left over from the Big Bang or interactions involving dark matter. While these ideas remain speculative, they highlight the profound mysteries that ultra-high-energy cosmic rays present. To unravel this mystery, scientists rely on sophisticated observatories designed to detect and study these elusive particles. Facilities like the Pierre Auger Observatory in Argentina and the Telescope Array in the United States use vast arrays of detectors to capture the rare interactions of cosmic rays with Earth's atmosphere. By analyzing the patterns and energies of these interactions, researchers hope to piece together clues about the origins of these particles. The study of ultra-high-energy cosmic rays not only deepens our understanding of the universe but also challenges our technological and theoretical limits. Each detection brings us closer to solving the puzzle of where these particles come from and what they can tell us about the most extreme environments in the cosmos. As we continue to explore this mystery, we are reminded of the boundless complexity of the universe and the endless questions it inspires. Now turning to the 19th mystery of the cosmos, we dive into the mind-bending concept of quantum foam, a strange and elusive idea that redefines our understanding of spacetime itself. At the smallest scales imaginable, far smaller than an atom, spacetime is thought to be a seething, frothy sea of fluctuations. This quantum foam suggests that the fabric of the universe is not smooth and continuous, as we once believed, but instead a chaotic, bubbling landscape where tiny particles and energy fluctuations pop in and out of existence in an instant. This radical idea challenges everything we know about reality. If spacetime is indeed a quantum foam, it means that the very foundation of the universe is unpredictable and constantly shifting. Imagine trying to measure the surface of a stormy ocean. Every wave and ripple would make it nearly impossible to get a clear picture. Similarly, the quantum foam makes it incredibly difficult to observe or test these fluctuations directly, as they occur on scales so tiny that they are far beyond the reach of even our most advanced instruments. The concept of quantum foam arises from the marriage of two of the most successful theories in physics: quantum mechanics and general relativity. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity explains the large-scale structure of spacetime. However, when we try to combine these two theories to understand the universe at its most fundamental level, we run into contradictions. Quantum foam is one of the ideas that attempts to bridge this gap, suggesting that spacetime itself has a granular, fluctuating nature at the smallest scales. One of the biggest challenges in studying quantum foam is the sheer difficulty of observing it. The fluctuations are thought to occur at the Planck scale, which is so small that it would take a particle accelerator the size of our galaxy to probe it directly. Instead, scientists rely on indirect methods, such as studying the behavior of particles or looking for subtle effects in the cosmic microwave background, the faint afterglow of the Big Bang. Even then, the evidence remains elusive, leaving quantum foam as one of the most tantalizing and untested ideas in modern physics. Despite these challenges, the concept of quantum foam opens up profound questions about the nature of reality. Could spacetime itself be made up of discrete, fluctuating units? What does this mean for our understanding of time, space, and the universe as a whole? As we continue to explore this mystery, we are reminded that the cosmos is far stranger and more complex than we can imagine, and that the answers to these questions may lie just beyond the edge of our current knowledge. Now turning to the 20th mystery of the cosmos, we delve into the enigmatic nature of time itself. Time, as we experience it, seems to flow in one direction forward. But why does time have an arrow? Why do we remember the past but not the future? This mystery lies at the heart of our understanding of the universe and challenges us to rethink the very fabric of reality. The concept of time's arrow is deeply tied to the idea of entropy, a measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time in a closed system. This means that systems naturally evolve from order to disorder, and this irreversible process gives time its direction. Think of a shattered glass. It's easy to break, but nearly impossible to reassemble perfectly. This one-way flow of entropy is what makes time feel like it's moving forward. But why does entropy increase in the first place? Some scientists believe the answer lies in the Big Bang. At the moment of the universe's birth, the cosmos was in an incredibly ordered, low-entropy state. As the universe expanded and evolved, entropy began to rise, creating the arrow of time we experience today. In this view, time's direction is a direct consequence of the universe's initial conditions and its ongoing expansion. Yet, the nature of time remains a puzzle. Is time a fundamental aspect of the universe, woven into the very fabric of space-time, or is it an emergent property arising from more basic physical processes? Some theories, like quantum gravity, suggest that time might not be fundamental at all. Instead, it could emerge from the interactions of particles and fields at the smallest scales, much like temperature emerges from the motion of molecules. The mystery of time also raises profound questions about our perception of reality. If time is not fundamental, does that mean our experience of past, present, and future is an illusion? Could time flow differently in other parts of the universe or in other dimensions? These questions push the boundaries of our understanding and remind us that time, something we take for granted every day, is one of the greatest unsolved mysteries of the cosmos. As we ponder the nature of time, we are left with more questions than answers. But one thing is certain: the arrow of time shapes our existence from the birth of stars to the fleeting moments of our lives. And as we continue to explore this mystery, we may uncover truths that redefine not only our understanding of the universe but also our place within it. Now turning to the 21st mystery of the cosmos, we explore a mind-bending idea that could revolutionize our understanding of reality, the holographic principle. Imagine for a moment that everything you see, touch, and experience, the vastness of galaxies, the complexity of life, even the fabric of spacetime itself, might be nothing more than a projection. A hologram. According to this radical theory, all the information in our three-dimensional universe could be encoded on a two-dimensional surface, like a cosmic DVD encoding a 3D movie. The holographic principle emerged from the study of black holes, those enigmatic regions of spacetime where gravity is so intense that not even light can escape. In the 1970s, physicist Jacob Bekenstein discovered that the entropy of a black hole, essentially the amount of information it contains, is proportional to its surface area, not its volume. This surprising finding suggested that all the information about what falls into a black hole could be stored on its event horizon, the boundary surrounding it. Later, physicist Leonard Susskind and others expanded this idea, proposing that the entire universe might operate in a similar way. In other words, the three-dimensional reality we perceive could be a projection of information encoded on a two-dimensional surface at the universe's boundaries. But what does this mean for our understanding of spacetime and quantum gravity? If the holographic principle is correct, it could provide a way to reconcile the two great pillars of modern physics: general relativity, which describes the large-scale structure of the universe, and quantum mechanics, which governs the behavior of particles at the smallest scales. These two theories have long been at odds, but the holographic principle suggests that spacetime itself might emerge from quantum interactions on a lower dimensional surface. This would mean that spacetime is not fundamental but rather an emergent property, much like temperature arises from the motion of molecules. The implications of this idea are staggering. If the universe is a hologram, it challenges our most basic assumptions about reality. It suggests that the three-dimensional world we experience is a kind of illusion, a projection of deeper, more fundamental processes. It also raises profound questions about the nature of black holes, the origins of the universe, and even the limits of human knowledge. Could we one day decode the cosmic hologram and uncover the true nature of reality? Or are we forever confined to experiencing only the surface-level projection? As we grapple with the holographic principle, we are reminded once again that the universe is far stranger and more mysterious than we can imagine. This theory pushes the boundaries of science and philosophy, inviting us to rethink not only the nature of spacetime but also our place within the cosmos. And as we continue to explore this extraordinary idea, we may find that the answers lie not in the stars above but in the hidden dimensions of reality itself. Now turning to the 22nd mystery of the cosmos, we delve into the enigmatic world of neutrinos and their puzzling mass. Neutrinos, often called the ghost particles of the universe, are among the most elusive and abundant particles in existence. They zip through space and even through you at nearly the speed of light, barely interacting with matter. For decades, scientists believed neutrinos were massless, as predicted by the Standard Model of particle physics, the framework that describes the fundamental particles and forces of nature. But in the late 1990s, a groundbreaking discovery turned this assumption on its head. Experiments revealed that neutrinos oscillate or change from one type to another as they travel through space. This phenomenon can only occur if neutrinos have mass, however tiny it may be. This discovery was a seismic shift in physics, as it directly contradicted the Standard Model, which had no provision for massive neutrinos. Suddenly, one of the most successful theories in science was incomplete, and physicists were left with a profound question. Why do neutrinos have mass, and where does this mass come from? The implications of this mystery are far-reaching. Neutrinos are thought to have played a crucial role in the early universe, influencing the formation of galaxies and the distribution of matter. Their tiny but non-zero mass could hold clues to the nature of dark matter, the invisible substance that makes up most of the universe's mass. Moreover, understanding neutrino mass could open the door to new physics beyond the standard model, potentially revealing deeper truths about the fundamental forces and particles that govern reality. One leading theory suggests that neutrinos acquire their mass through a mechanism involving a hypothetical particle called the sterile neutrino. Unlike the three known types of neutrinos, sterile neutrinos would interact only through gravity, making them even more elusive. Another possibility is that neutrinos get their mass from interactions with the Higgs field, the same field that gives mass to other particles like electrons and quarks. However, the exact mechanism remains unknown, and experiments around the world are racing to uncover the truth. The search for answers has led to the construction of massive detectors deep underground, where scientists can observe neutrinos with minimal interference from other particles. Projects like the Deep Underground Neutrino Experiment, or DUNE, aim to study neutrino oscillations in unprecedented detail, shedding light on their masses and properties. These efforts could not only solve the neutrino mass puzzle, but also revolutionize our understanding of the universe. As we explore this mystery, we are reminded once again that even the tiniest particles can hold the keys to the cosmos's greatest secrets. The neutrino mass puzzle challenges us to rethink the foundations of physics and pushes us to uncover new layers of reality. And as we continue to probe the universe's hidden depths, we may find that the answers lie not in the vastness of space, but in the subtle, ghostly dance of these enigmatic particles. Now turning to the 23rd mystery of the cosmos, we venture into the vast, empty expanses known as cosmic voids. These regions, which stretch across hundreds of millions of light years, are some of the most striking features of the universe's large-scale structure. Unlike the dense clusters of galaxies and filaments that make up the cosmic web, cosmic voids are nearly devoid of matter, creating immense pockets of emptiness that defy our expectations of how the universe should look. At first glance, these voids might seem like mere empty spaces, but they play a crucial role in shaping the cosmos. They act as the counterbalance to the dense regions of the universe, influencing the way galaxies form and evolve. The presence of voids helps us understand the distribution of matter on the largest scales, revealing patterns that trace back to the early universe. Yet, their existence also raises profound questions. Why are these voids so empty, and what do they tell us about the forces that shaped the universe after the Big Bang? One of the most intriguing aspects of cosmic voids is how they challenge our understanding of galaxy formation. According to traditional models, galaxies should form more readily in regions where matter is densely packed. But observations show that galaxies can still form on the edges of voids where matter is sparse. This suggests that the processes driving galaxy formation are more complex than we once thought, involving not just gravity but also the interplay of dark matter, dark energy, and the mysterious forces that govern the cosmos. The study of cosmic voids also sheds light on the distribution of dark matter, the invisible substance that makes up most of the universe's mass. While voids appear empty, they are not entirely devoid of matter. Instead, they contain a faint trace of dark matter spread thinly across their vast expanses. By mapping these faint traces, scientists can gain insights into the nature of dark matter and its role in shaping the universe. This, in turn, could help us unravel some of the deepest mysteries of cosmology, from the behavior of dark energy to the ultimate fate of the cosmos. As we explore these enigmatic regions, we are reminded that even the emptiest parts of the universe hold secrets waiting to be uncovered. Cosmic voids challenge us to rethink our assumptions about the cosmos and push us to develop new tools and techniques for probing the universe's hidden structures. And as we continue to study these vast, empty spaces, we may find that they hold the key to understanding not just the universe's past but also its future. Now turning to the 24th mystery of the cosmos, we delve into one of the most profound and enigmatic questions of all, the nature of consciousness in the universe. Is consciousness merely a byproduct of complex biological systems, or could it be a fundamental property woven into the very fabric of reality? This question challenges not only our understanding of life and intelligence, but also the nature of existence itself. One compelling theory that attempts to address this mystery is panpsychism. This idea suggests that consciousness is not exclusive to humans or even to living beings, but is instead a basic feature of the universe, present in all matter to some degree. According to panpsychism, even the smallest particles possess a form of primitive consciousness, and complex systems, like the human brain, emerge from the combination of these fundamental conscious elements. While this might sound like science fiction, panpsychism offers a radical perspective that bridges the gap between the physical and the mental, proposing that consciousness is as fundamental as space, time, or matter. The implications of panpsychism are staggering. If consciousness is indeed a fundamental property of the universe, it could reshape our understanding of life and intelligence. It suggests that consciousness might not be limited to Earth but could exist in other forms throughout the cosmos. This raises fascinating questions about the nature of extraterrestrial life and whether other planets, stars, or even galaxies might harbor some form of awareness. Could the universe itself be conscious in some way, perceiving its own existence through the myriad forms of life and matter it contains? Another intriguing aspect of this mystery is how it intersects with our understanding of the cosmos. If consciousness is fundamental, it could play a role in the very structure of reality, influencing the way the universe evolves and organizes itself. Some scientists and philosophers speculate that consciousness might be linked to the quantum realm, where particles exist in states of probability until observed. Could the act of observation by a conscious being be what collapses these probabilities into definite states? This idea, while speculative, hints at a deep connection between consciousness and the physical laws that govern the universe. Of course, these ideas are not without controversy. Critics argue that panpsychism and similar theories lack empirical evidence and are difficult to test scientifically. Yet, the mystery of consciousness remains one of the greatest unsolved problems in both science and philosophy. As we continue to explore the cosmos, we may find that understanding consciousness is not just about unraveling the workings of the human mind, but about uncovering the very nature of reality itself. As we ponder these profound questions, we are reminded that the universe is not just a collection of stars, galaxies, and dark matter, but a tapestry of mysteries waiting to be explored. The nature of consciousness challenges us to think beyond the boundaries of traditional science and to consider the possibility that the cosmos is far more interconnected and alive than we ever imagined. And as we continue to seek answers, we may discover that the key to understanding the universe lies not just in the stars above, but within the depths of our own awareness. Now turning to the 25th and final mystery of the cosmos, we venture into one of the most mind-bending ideas of all, the simulation hypothesis. Could our universe, with all its galaxies, stars, and life, be nothing more than an incredibly advanced computer simulation? This provocative idea challenges not only our understanding of reality, but also the very nature of existence itself. The simulation hypothesis suggests that everything we perceive as real, our thoughts, emotions, and the physical world around us, might be the product of a highly sophisticated simulation created by an advanced civilization. This idea gained traction in the early 2000s when philosopher Nick Bostrom proposed a thought experiment suggesting that future civilizations with immense computing power might choose to run simulations of their ancestors. If this is true, the odds are that we are far more likely to be living in one of these simulations than in the original, base reality. Supporters of the simulation hypothesis point to several intriguing arguments. One is the rapid advancement of technology, particularly in virtual reality and artificial intelligence. If humanity continues to progress, it's conceivable that we could one day create simulations indistinguishable from reality. If this is possible, it raises the question, why wouldn't a more advanced civilization have already done so? Another argument comes from the peculiarities of quantum mechanics, where particles behave in ways that seem almost like the universe is rendering reality on demand, much like a computer processes information. However, the simulation hypothesis is not without its critics. Many scientists argue that the idea is untestable and lacks empirical evidence. After all, how could we ever prove that we are living in a simulation if the simulation itself controls all our perceptions and tools of measurement? Others point out that the computational power required to simulate an entire universe, down to the smallest particles, would be beyond anything we can currently imagine, making the idea seem far-fetched. Despite these challenges, some researchers have proposed ways to test the simulation hypothesis. One approach involves looking for potential glitches or patterns in the fabric of reality that might hint at underlying code or computational limits. For example, if the universe operates on a finite grid, there might be detectable anomalies in the behavior of particles at extremely small scales. Another idea is to search for evidence of mathematical constraints or symmetries in the laws of physics that could suggest a designed system. The simulation hypothesis also raises profound philosophical questions. If we are living in a simulation, what does that mean for free will, morality, and the purpose of life? Are we merely characters in someone else's story, or do we still have agency within the simulation? And if we could somehow confirm that we are in a simulation, how would that change our understanding of ourselves and our place in the cosmos? As we conclude our exploration of the 25 mysteries of the expanding universe, the simulation hypothesis reminds us that reality may be far stranger and more complex than we ever imagined. Whether or not we are living in a simulation, these mysteries challenge us to think beyond the limits of our current knowledge and to embrace the infinite possibilities of the cosmos. The universe, in all its wonder, continues to inspire us to ask the deepest questions and to seek answers that may one day redefine our understanding of existence itself. Now turning to the conclusion of our journey through the 25 mysteries of the expanding universe, we find ourselves standing at the edge of the known and the unknown. These cosmic enigmas, from the elusive nature of dark energy and dark matter to the mind-bending possibilities of the simulation hypothesis, remind us just how much we have yet to discover. Each mystery challenges our understanding of space, time, and reality itself, pushing the boundaries of human knowledge and inspiring us to look deeper into the cosmos. What makes these mysteries so compelling is not just their complexity, but the way they ignite our curiosity. They remind us that the universe is far stranger and more wondrous than we could ever imagine. Whether it's the unexplained pull of the Great Attractor, the puzzling alignment of the cosmic microwave background, or the haunting silence of the Fermi paradox, these questions invite us to explore, to question, and to dream. They remind us that science is not just about finding answers, it's about embracing the journey of discovery. As we reflect on these 25 mysteries, it's clear that the universe is a place of infinite wonder. Every question we answer leads to new questions, and every discovery opens the door to even greater mysteries. This is the beauty of science and exploration. It's a never-ending adventure, one that keeps us humble, curious, and inspired. So, what do you think about these cosmic mysteries? Do you have a favorite or perhaps a theory of your own? Share your thoughts in the comments below. We'd love to hear your ideas and spark a conversation about the infinite wonders of the cosmos. And if you enjoyed this journey through the mysteries of the universe, don't forget to subscribe and hit the notification bell so you never miss an exploration into the unknown. Together, let's keep asking the big questions and uncovering the secrets of the cosmos. After all, the universe is waiting and its mysteries are calling.